Hello everyone, welcome to mobile computing tutorial. In this video, we will discuss GSM frequency allocation. GSM generally uses 900 MHz band. Out of this, 890 to 915 MHz are allocated for uplink. Uplink means mobile station to base station. Here we can see the figure. So in this figure, you can see the uplink and downlink frequencies. So here this band of frequencies, that means 890 megahertz to 915 megahertz frequency band, this is used for uplink. Uplink means mobile station to base station. So we have 124 channels are available in this band of frequencies. So then again 935 to 960 megahertz for the downlink frequencies. So for this frequency range between 935 to 960 megahertz frequency ranges are used for the downlink, that means base station to mobile station. You can see the range of frequencies in this picture. 935 to 960 megahertz range of frequencies are used for downlink in the case of 900 megahertz band. Each way, the bandwidth for the GSM system is 25 megahertz. So the bandwidth for the total bandwidth for uplink and downlink, so each range of frequency has 25 megahertz bandwidth. That means how to calculate this 25 megahertz? 915 minus 890 and 960 minus 935, you will get 25 megahertz bandwidth. We have 125 channels are available for uplink and downlink in each band of frequencies. You can see in this picture, for the uplink we are using 890 to 915 megahertz band of frequencies. In this band of frequencies, we are divided the band of frequencies into 124 channels. Channel number 1, channel number 2, etc. up to 124 channels. Actually, we have 125 channels are available, but in practical case we are using only 124 channels. Channel number from 1 to channel number 124, these are called transmission channels. So each channel having a bandwidth of 200 kilohertz. You can see each channel having a bandwidth of 200 kilohertz. The ARFCN number, the next specification is the ARFCN number. ARFCN means absolute radio frequency channel numbers. These are the ARFCN number. ARFCN number will start from 1 to 124. That means if the ARFCN number 1 for channel number 1, then ARFCN channel number 2, then etc. channel number 3. So the ARFCN channel number denotes a forward and reverse channel pair which is separated in frequency by 45 megahertz. So each uplink and downlink channels will be separated by 45 megahertz frequency. We have an equation, we have two equations for the uplink and downlink frequencies. That is mobile to base and base to mobiles. We are using two equations to find the frequency. So we have the equation mobile to base is called Ft of n. The n is the ARFCN number or channel number. Value of n may be 1, 2, etc. up to 124. So in the case of mobile to base, we have the equation Ft of n is equal to 890.2 plus 0.2 into n minus 1 megahertz. So if the value of channel number is 1. So assume the channel number will be 1. What will be the equation? Ft of 1 equal to 890.2 plus 0.2 into 1 minus 1. That will be the frequency of the channel number 1. Then in the case of base to mobile, we have another equation. Ft of n is equal to Fr of n plus 45 megahertz. You have to replace the equation with Fr of n is equal to Ft of n plus 45 megahertz. So please note this equation. In this equation you have to replace some letters with you have to replace this Ft of n with Fr of n. So Fr of n is equal to Ft of n. Ft of n. Ft of n means the mobile to base frequency. So Ft of n plus 45 megahertz. We have studied there is a 45 megahertz difference between the Ft of n and Fr of n megahertz frequencies. So this equation will be Fr of n is equal to Ft of n plus 45 megahertz. Value of n will be 1 to 124. In practical implementation, a guard band of 100 kHz is provided at the upper and lower end of the GSM 900 MHz spectrum, and only 124 duplex channels are implemented. So as we said, in practical case only 124 duplex channels are implemented. Also some new bands are added to the basic 900 MHz GSM band. So these new bands are 1800 MHz and 1900 MHz. So new bands like 1800 MHz and 1900 MHz bands are added to the basic GSM bands. The 1800 MHz band uses 374 duplex channels. In 900 MHz band we have only 124 duplex channels. GSM 900 uses the 4-cell repeat pattern for the frequency reuse cell sets. So we have the picture of 4-cell repeat pattern. In this picture you can see this is the cell 1, this is cell number 2, this is cell 3, this is cell 4. This is the 4-cell repeat pattern for the frequency reuse. Then this 4-cell will create a cluster with k is equal to 4. So we have another cluster here 1 2 3 4 frequency 1 2 3 4, and we have then another cluster is present 1 2 3 4. So in most cases each cell is divided into 120-degree sectors with 3 base transceiver subsystems in each cell. So each cell is divided into 120-degree sectors. So cell 1 is divided into 3 120-degree sectors, then cell 2 is divided into 120-degree sectors. So each cell contains 3 sectors. So in 4-cell repeat pattern we have 4 into 3, we have 12 sectors available. So each base transceiver has a 120-degree antenna. These 12 sectors share the 124 channels. Then to share the bandwidth for users, GSM uses a combination of TDMA and FDMA encoding. One or more carrier frequencies are assigned to each base station. Each of these carrier frequencies is then divided in time using a TDMA. So in GSM we are using a combination of TDMA and the fundamental unit of time in this TDMA scheme is called a burst period, and it lasts approximately 0.577 millisecond. So please note the fundamental unit of time in this TDMA scheme is called a burst period, and it will last approximately 0.577 millisecond. So we have the day is present here. So this is called a burst period. 8 based periods are grouped into a TDMA frame for approximately 4.615 milliseconds. So, in this picture, each channel is divided into 8 based periods or 8 time slots. So in this picture we can see each frequency channel is divided into 8 TDMA frames. So in this picture you can see each frequency channel is divided into 8 time slots. So in each time slots we have a database. So the database contains 156.25 bit periods. The fundamental unit of time in this TDMA scheme is called a based period and it lasts approximately 0.577 millisecond. From this picture you can see the data based period. So this is the data based period, that the duration of a data-based period 156.25 bit period is 0.577 millisecond or 576.9 microsecond. Each channel is divided into 8 time slots. Each time slot contains one data-based period. So 8 based periods are grouped into a TDMA frame. So in one TDMA frame we have 8 data based. Then what will be the value of, or what will be the time duration of one TDMA frame? So one TDMA frame approximately 4.615 millisecond. That means 0.577 into 8, that is equal to 4.615 millisecond, which forms the basic unit for the definition of logical channels. So one channel contains 8 data based. Channels are defined by the number and position of their corresponding based periods. A traffic channel TCH is used to carry speech and data traffic. Traffic channels are defined using a 26 frame multi-frame. So the concept of multi-frame is here. So a traffic channel TCH is used to carry speech and data traffic. Traffic channels are defined using a 26 frame multi-frame or group of 26 TDMA frames. So a multi-frame contains 26 TDMA frames. We have one TDMA frame contains 8 time slots. So each TDMA frame contains 8 based periods. I repeat, each multi-frame contains 26 frames. That means 26 TDMA frames, and each frame contains 8 based periods. Out of the 26 frames, 24 are used for traffic. One is used for the slow associated control channel. It is called SACCH, and one is currently unused. So what is SACCH? The SACCH channel has the functions like timing advance of data, transmit power control, and transmission of signaling data, and radio link supervision measurements. So these are the functions of SACCH. Then we have the basic unit is called a database is present. So one time slot of frame contains one based period. The first 3 bit of the time slot or based period is called tail bit. The tail bits are present at the start and end of every time slot. Distinguish one time slot from another. It identifies beginning and end of the based. Then next 57 bit is data. That means data. This is the actual information to be transmitted. So this 57 bit data contains the information. Out of 156.25 bits, 114 are information bearing bits that are transmitted as 257 bits sequences close to beginning and end of the time slot. In this figure you can see this is the first 57 bit of data information and another 57 bit of data information. So 57 plus 57, that is equal to 114. So these 114 bits are the information. Then next bit is the steal bit. Only one bit is present, steal bit. This bit helps base station to distinguish whether the coded data is control or actual information. So this stealing bit is used to distinguish whether the coded data is control or actual information. At the time of urgency, control bits are also sent using voice channel. At that time, stealing bit becomes 0, indicating coded data carries control information. So if the stealing bit is 0, it represents the data is a control information. So the next 26 bit is called mid amble. So this consists of 26 bits training sequence. It helps the adaptive equalizer in mobile or base station receiver to analyze radio channel characteristics before coding. It gives the amount of fading the channel provides, helping to decide which equalizer is to be used. The function of equalizer is to reduce inter-symbol interference to allow recovery of the transmit symbols. So the function of equalizer is to reduce the channel or signal interference. Then we have another bits. It is called guard bits. A guard time of 8.25 bits is provided at the end of every time slot to prevent overlapping with the next time slot, preventing actual information from getting tampered. So these guard bits are used to prevent information by avoiding overlapping of the overlapping between the time slots. That is the end of this topic. Thank you.